Okay, welcome. Thank you for coming. So, as in any physical theory, we need to specify what we measure. So, in the last class, I showed you that scattering experiments in general measure fluctuations inside the system. Now, we're going to talk about transport. So, for example, we want, electrical conductivity, thermal conductivity, Seebeck effect. All these quantities are magnetic susceptibility. All these quantities are related to transport, frequency dependent. So what is the answer? I will tell you the answer, and then we'll see how to get there. So this is a linear response. So suppose I have some operator B. I will give you a specific example. Non-equilibrium in the presence of an external probe, in other words, minus the equilibrium value. Let me write it like this. B equilibrium, it's equal to I over h bar times the integral from minus infinity to t dt prime of the expectation value of the commutator of B of R T with A of R prime T prime. And here I will put some little index I times A I of R prime T prime. Okay, I have a lot of explaining to do. So what is B? B could be, for example, current. I could measure the DC conductivity or the optical conductivity, whatever, but it's the electrical current. I could also add the heat current, GH. Then I want to know the thermal response, the thermal current. Or B could be, for example, the spin or the magnetization. So let's say spin, for example. So then it would be a vector. So this is just one component, spin. Now the idea is that there's some external probe that external perturbation I put in. So this external perturbation, if you want the delta H of T, the change in the Hamiltonian due to the perturbation, will be equal to minus integral d cube of r prime of this operator here. So I would call AI of r prime and little ai of r prime t prime. Okay, let's give you some example. So for example, if I'm looking at the response to an electromagnetic field, then this A would be J, and this little a would be the vector potential A. Okay, that's the coupling. I will come back to that later, how the electromagnetic field couples to matter. But if you've done some advanced quantum mechanics, you know that this is J.A. Now we are in the semi-classical limit, which means that A here is a classical operator. It's an object that commutes with everything. Okay, so if you have a large electromagnetic field, as you know, a large electromagnetic field has lots and lots of photons, and so I can, if one photon or less doesn't change anything. So this is a large field, and this is classical. That's why I wrote a little a, and that's an operator. So if I have a thermal gradient, Then I will have some heat, a current, times the gradient of temperature divided by temperature. If I'm looking at the response, if I'm coupling to some external magnetic field, then this little a is a spin operator times an external magnetic field, which again is classical. It can be time dependent. Okay? So the Hamiltonian depends on temperature, on time because of, okay, this should be a T here, because of this object here, this external field that depends on time. And that's an operator. Now you will see that how it depends on time at the end. So let me give you a wrong derivation of this. So it's just to get an idea of what's going, and then I'll give you the correct derivation. So you know that the evolution operator is the Hamiltonian. So let me write the Hamiltonian H, okay, the total Hamiltonian H as the Hamiltonian of the system, that I write with an H like that, plus this external perturbation delta H of T. Now, if I want to know what happens to B, then you know that the Heisenberg representation, the evolution operator, is e to the IHT, where this the full H, so I have H plus delta H times the time, and I have B, and I have e to the minus I H plus delta H times T, where delta H contains this object. So if I expand to first order, you see I will get a commutator. I will get delta H on this side and delta H on that side. So that's why I have a commutator like this. Now, why is this derivation wrong? Well, because if delta H depends on time, and delta H does not commute with the big H, I cannot just expand the exponential trivially, okay? So we have to go back a little bit and talk about the Schrödinger and Heisenberg representations, and then go to the interaction representation. So the interaction representation will allow us to treat this. And also when we treat this thing that's a full Hamiltonian, we can also divide it in two pieces and use the interaction representation again. But for now, it's only this that matters.
André-Marie, shouldn't we say, excuse me, shouldn't we say that in any case, the exponential itself is wrong, right? If it's
yes, I mean, exactly. I cannot write it like this.
Right.
Good point. So en français, ça c'est la représentation de Schrödinger, la représentation d'Heisenberg et la représentation d'interaction. In English, it can be the Schrödinger picture, Heisenberg picture, and interaction picture, or Heisenberg representation, Schrödinger representation, and interaction representation. But in French, we don't see l'image de Schrödinger. Okay. Any question? Okay, so as you know, the Hamiltonian is the generator of infinitesimal time translation. So I'll start with the Schrödinger picture, Schrödinger representation, but assume a general Hamiltonian. So the Schrödinger equation is IH bar d dt of psi Schrödinger of t is equal to, I will write some general time-dependent Hamiltonian times psi Schrödinger of t. So if h is independent of time, that's the only case where we can write that that the psi s of t is equal to exponential of I h times t times psi s of 0. Okay. If h is independent of time, we cannot do this. We'll see why in more detail later, but basically it's related to the fact that h here at different time can be a different object, so that it does not commute with itself. Okay, h at time 0 and h at time t don't necessarily commute with each other. So let's just write the general solution as psi s of t. I don't know exactly how to get that solution, but I will write this as a unitary evolution operator, u of t, t0 times psi Schrödinger of t0. Okay. What we know is that the probability is conserved, so that this has to be unitary. Now, if I look at let me remind you of the definition of the adjoint. Okay, so if I take some operator, let me call it anything, let's say big K, that acts on psi, then I can take the matrix element with any other state phi like this. Now, if I want the adjoint of this, the operator, the way to do that is to notice that K phi, by definition, I will write this as psi K dagger phi. Okay, so that's what is meant by the adjoint. So it means here that if I want to know psi, oops, sort of out of space, psi s of t, it will be equal to psi Schrödinger of t0 times the u adjoint of tt0. Okay, just using this. Now, what's the relation between the Schrödinger and the Heisenberg picture? It's very simple. It's just that we say that at time 0, psi Schrödinger at time 0 is equal to psi Heisenberg at time 0. And then we write that the result should not be dependent on the way we do the mathematics. So it means that if I write psi Heisenberg at time 0, then this is the same as psi Schrödinger at time 0. So it means that I can write u dagger of t0. Then I compute the expectation value of any operator. in the Schrödinger picture times u of t 0 times the psi Heisenberg of 0. Okay. So what happens then is that this should be equal to psi Schrödinger of t times operator times psi Schrödinger of t. So in the Schrödinger picture, it's the wave function that's evolving. And in the Heisenberg picture, it is the operator that is evolving. Okay, this I can write as operator in the Heisenberg picture as a function of time is just equal to this object. Okay. Very simple. So in the usual case where h is constant, you recover what you know. Okay, now what about the interaction representation? Because this is what we will want to do here. So in the interaction representation, both the wave function and the operators will evolve with time. If you do magnetic resonance, nuclear magnetic resonance, for example, or if you're doing quantum computing, then going to the interaction representation is often referred to as going to the rotating frame. Just because in in nuclear magnetic resonance, you have some spins that rotate, and then you apply some external probe, and the probe will make the field, will make the spin turn around, but it's turning around while it's rotating all the time. So they say they go to the rotating frame to have the spin fixed. Okay. So so we will take the psi in the interaction picture at time 0 to be the same as this. So the idea is just the following: is that we look at this evolution operator, this u of t, and then let me start with 0 here. U of t 0 is equal to u. Let me get this straight. E to the minus I h0 t times u interaction of t 0. So this is just a definition of this evolution operator. So if time is larger than 0, this is what happens. Now in the other case, if you get t0 less than time 0, then I have u interaction of 0t times e to the I h0 t0. Okay. Now I'm almost finished. What I need to do now is to write an equation of motion for this this object. So I h bar ddt of u of t0. I just have two terms. So I have I h bar minus I. So I have I was a little bit too fast with the derivatives there. So I times I means it drops. So I have h0 times e to the minus I h0 t plus I h bar times e to the minus I h0 t. Sorry, I mean h bar equals one guy. So I need to divide by h bar, and this h bar disappears. Okay, finally, I'll get it straight eventually. Okay, so and here I have ddt of u interaction of t 0, and here, oh, sheesh, what am I doing? I'm missing the ui here. Ui. Okay. And on the right hand side, I have the Hamiltonian. So the Hamiltonian now is h0 plus some external perturbation that I wrote here at the beginning. Okay, that was these ai or ri. So I have delta I h of t times e to the minus I h0 t times ui, as always of t0. Perhaps you don't see it anymore, but okay.
No, it's okay. It's right on the limit.
It's okay?
Yeah.
So you see what happens is that this here simplifies with this part here. Okay. And now I have that IH bar ddt of ui of t0 is equal to, now I multiply by e to the I h0 t over h bar both sides. So that gives e to the I h0 t over h bar times u times delta h. What am I doing? Delta h of t times e to the minus I h0 of t over h bar times u interaction of t 0. So you see, even if delta h was not dependent on time, suppose that the delta h, this external probe, is any Hamiltonian, it's not necessarily depending on time. It has become dependent on time now. So the equation of motion, I will define the evolution of operators in the interaction representation. So in the interaction representation, the operators, here the perturbation, evolve with the Heisenberg equations for h0, for the unperturbed part. So I will write this as delta I h of t. Okay, sorry, I'm erasing this, but you have to remember that we're just evolving with the Heisenberg equations of motion for the unperturbed system. So very important here that IH bar d dt of this is delta H of t times u I of t 0. And now I will do just the same as what I did with the Heisenberg picture. Now we will make sure that the expectation value of operators evolves, gives the same result, whatever picture I take. Okay. So if I want to compute the expectation value of psi Schrödinger of t, so it's psi Schrödinger of 0 times u of t 0, but that is equal to, that's equal to u dagger, okay? Like I have here. So u dagger now is ui dagger of t 0 times e to the plus I h0t. Okay, so that's just this that I applied here. Now I have my operator whose expectation value I want to compute. So sorry, I have to take two lines. So I take the operator in the Schrödinger picture, and now I evolve again with this. So I get e to the minus I h0t over h bar times ui of t 0 psi Schrödinger of 0, which is the same as psi interaction at time 0. So you see what happens is that the operators, the OS, again evolves with the non-interacting Hamiltonian, or with H0, just like here. So this, I write here I to remember that's an interaction picture. So in the interaction picture, I have a psi interaction of 0 times the u dagger of t 0 times, now instead of O Schrödinger here, I have O interaction of t times u I of t 0 times psi interaction of 0. Okay. So the well, you certainly don't see, but you can guess what's on the right hand side, right? So the wave function evolves and the operators as well. Okay. So here I need to put UI. So to go further, and I'm almost done. To go further, I need to solve this equation. Okay. So I will tell you what is the general solution of this equation, and I will prove it later. For now, we'll just use the first order, because remember, we just want to treat the external perturbation, which is electric field or magnetic field, whatever. We want to treat the external perturbation to first order. So we just need to solve this to first order. Okay. So the general solution of this is that U interaction of t, and now the time here can be anything. So t0 is equal to the time ordered product of the exponential of minus I over h bar, with the integral of t0 to t of delta h interaction of t prime dt prime. Okay. So time ordered product means you expand this quantity and you put all the operators in a sequence where the later time is to the left. So why is that? It's not obvious. But you see that if this was time independent, you would recover the usual evolution operator. So now I don't want to prove this right now, but we will use this a lot later. So when we need it, I will prove it. But for now, what we need is just the first order solution. So what is the first order solution of this? I integrate on both sides, so I can put some arbitrary time here, t0, and if I want to have some t0, just given the definition I gave, ui of t0 will be u of t0, I'm sorry, where t0 is less than 0. The full evolution operator will be e to the minus I h0 t over h bar times u I of t0 times e to the I h0 t over h bar, where I have used that for any of these evolution operators, whether it's the interaction or this one, u of t at t0 is equal to u I of t0 times u I of 0 t0. You evolve up to time 0 and then from 0 to t. Okay, this follows from this and from the definition I gave of the ui when t0 is less than 0. So this is t0. Okay, so that I put a t0 here. Then all that I need to do is to solve this to first order, and it's easy to do by just iteration. So if I integrate on both sides, okay, from t0 to t, I get I h bar u of t0 minus u of t0, okay? ui of t0, because I integrate from t0 to t. So this ui t0. And then I get equal. So I will multiply by minus I and divide by h bar. So I have a minus I over h bar. Then I can get rid of this. Times the integral from t0 to t of delta hi of t prime dt prime. Okay. But what is ui of t0? It's 1, okay? Because I have not evolved anything. So this operator is minus 1. Minus 1. So let me put the 1 on the other side. What would I do without an eraser? Huh? So ui of t0 is equal to 1 minus this. Oh my God. You were sleeping. ui.
No, I was trying to understand why this was missing.
Okay, don't hesitate. I make mistakes all the time. Okay, so when I do crazy things, you have to tell me. I'm not following notes, so I just make mistakes. Okay, so now you agree with this, okay?
Yeah, but on the line above, is it missing it also in the exponential?
No.
No?
This
Okay.
is the exact result. Okay. So, but anyway, you don't need this for now. So if I solve this by iteration, if I want to know this evolution operator to first order in delta H, then I can just replace this ui by 1. Okay. I can say I was anticipating. So if I replace this evolution operator by 1, then I get the first order result. I get this is 1 minus this. And this is what I get if I expand this to first order. Okay. So now we want to go back to seeing what happens to B if I have some external probe, external perturbation, I should say. Okay. So I want the difference here. So I want the first order term. So that will come from this. So if you go back to this, and now my non-interacting Hamiltonian is the full Hamiltonian of the system. Okay. And the perturbation delta H is what I wrote at the beginning. Okay. So here on the left, I need U dagger, and I expand to first order. So I get IH bar times delta H and delta H of T prime. Okay, now it has to evolve with the Hamiltonian of the full system because my unperturbed Hamiltonian is the Hamiltonian of the full system. So that's why I get this on the whoops, that IH bar dagger. I should have this on the left, no? U dagger. I get once I will get delta H on this side, and the other time I will get delta H on that side. Okay, but okay. The reason it's like this is because my delta H of t was equal to minus integral d cube r prime of a of r prime I ai of r prime t prime. Okay, t, sorry. So this is minus here. So that's why I'm left with just I. And here I'm missing the integral over r prime clearly. So we have an integral d cube r prime.
And also you didn't close the expectation value.
And I didn't close the expectation value. Oh, I'm so bad. Okay, is it okay? Okay.
Also, there's a missing arrow on the r in your integral.
I have the integral and the d cube r prime.
Yeah, on the left side of your equality, the r is a vector.
Okay, so I should
remove
the arrow to be consistent. Okay. These are all vectors, and I have so much to erase. I'm not putting the vector sign. You have to imagine it's bold or something. Okay. Okay, now there are many objections you can raise to this. Okay, one is that we have looked at the evolution operator using unitary evolution, and we want to describe dissipation. So how do we get something irreversible here, despite the fact that we've taken a unitary evolution? Well, we know how. I mean, in correlation functions, if you take the infinite size limit, then the evolution becomes, there's some damping. The evolution becomes irreversible. Okay, that's one way to look at it. Okay, another objections you may raise is what about heating? You know, if I apply an external electric field, there will be some joule heating, right? There will be some heat generated. So where is the heat going? Well, the answer is that the heat shows up only to second order in the electric field. Okay, because joule heating is proportional to E squared. And what happens if I compute this second order term in a closed system? Well, you will find that the second order term diverges because you're pumping heat, and so it will grow with time. So it's bad news. Okay, so the way to get around that is to assume, for example, that you have or you can put in the calculation a phonon bat that interacts with your system, and you assume stays in equilibrium. Okay, then that forbids the second order term from increasing linearly with time. Okay, another way to do it is to put for example, you have a wire like this. You put the transverse temperature gradient, and you assume that the boundaries remain in equilibrium. There will be some temperature gradient because the inside wants to heat up. So the heat is going up, but you're maintaining the sides your system in equilibrium. So there will be some small temperature gradient in your system. Okay, the temperature gradient in your system will be like this. So, I mean, okay, I'm looking, the wire is like this. So it wants to heat up, but I'm maintaining this at fixed temperature. So there will be some parabola here. And you can make sure that actually this will influence the response only to second order again. So to first order, it's a good way to do things. Then there's some other criticism of this that I'm trying to remember now, and I forget. Just a second. I've not written it there. It's in the notes. So there's a famous formula to compute connectivity that's called the Kubo Formula, which is just a special case of this. And we will see that the response, which is given by this commutator, is related to the fluctuations. And the fluctuations, there's no commutator. So now, if you have translational invariance, well, let me write this in a more general way. So this will be integral from minus infinity to infinity of chi retarded, retarded is on top, chi retarded of, I will write a B A to remember that this is a commutator like this, of R minus R prime. You see, if I have a space translation invariance, it can depend only on the difference, R minus R prime, T minus T prime, of A of R prime, T prime, where I have defined the chi retarded of B A of R minus R prime, T minus T prime, to be equal to this commutator times I over H bar times theta of T minus T prime. Okay, because this goes to up to T, and this goes to infinity. So if I take the integral to infinity, I put theta function here. So you recover, you see, you find the structure that we had before for the retarded response. So that's why I put retarded.
But now there's no sum over I as we had before.
Yeah, I should put AI to be rigorous here. Okay, so that's it for today. What I suggest for homework is that you do the last exercise in the section that is just before part 2. Okay, you have in the notes, you have part 1, then you have part 2. If you look at the last exercise of there's an exercise section between part 2. If you look at the last exercise, please do that. You can take 2 weeks to do it, but it's an easy problem. I mean, once you spend 1 hour or 2 at most, you should be able to do it. I mean, if you need more than a couple of hours, ask me or ask Chloe, because it's not worth spending so much time. I'm asking you enough to give me these copies of the notes. Okay. So
just to be sure, it's the section 6.1. So the one in the 2 exercise in the homework 2.
there should be several, there's a section that should be called exercise, and depending on the version of the notes that you have, it can have a different chapter name. But it's just before part 2. So
is it the
that
problem
piece is
about the
invariant.
Kubo correlation?
No,
No,
it just
seems
has to do with showing that the branch cut, the value of the function at the branch of a retarded function at the branch cut is given as the difference between the retarded and the advanced function. You see this? Or perhaps I didn't look very well. Okay. Can you share the notes? Someone shares. I will stop the recording.
I can share it.